Cool. Did that start the recording? Could somebody confirm that? I've never actually done this before. Sweet. Okay, so a few things before we start. First, congratulations on making it through EECS 281. This is by no means an easy class, and I think you guys have all shown some great skill by just making it this far, and you should all be proud of yourselves. And with that said, what we're going to be going over today are going to be some of the more advanced topics that you probably won't even see covered in other courses here at UMich. But they're just things that I think are very, very cool. And at the very least, they are certainly helpful if you want to get into some advanced C++ programming in the future. So that said, I'm going to try to go over this at a reasonable pace, reasonable being rather slow. And if you have any questions at any time, please feel free, put something in the chat. I have it open. Or just unmute your mic and, shout it out. Stop me at any time. So without any further ado, here's what we're going to be going over today. I think we'll make it through all of this. I've allocated 2 hours for this, and I'm pretty sure we'll be able to get through all of it in time. But if we don't, I'll just go over and feel free to leave. Everything will be in the recording. So the first thing we're going to talk about is move semantics. And C++ move semantics, they're kind of based around the idea of the rule of 3. So if you were at UMich when you took your course before EECS 281, which at UMich would be EECS 280, you would learn about the rule of 3, which is if you're defining a custom class or struct, and you need to define any one of the following, those being a copy constructor, a copy assignment operator, or a destructor, that you probably need to define them all. And if I'm remembering correctly from EECS 280, this usually was referring to the managing of dynamically allocated memory. So if we have some class that in a constructor calls new on some chunk of memory, then normally what we would want to do in the copy constructor and copy assignment operator is do a deep copy of the allocated data rather than just a shallow copy of just the pointer itself. And this makes sense because we don't want to just copy the pointer value. We want to actually copy the data that's being pointed to. So that would be what we would override the copy constructor and copy assignment operator to do. And in the destructor, of course, if we called new in the constructor, we're going to probably need to call delete in the destructor. So that's the idea of the rule of 3. If anybody has any questions on that, go ahead. This is just a general idea from EECS 280 that hopefully at least some of you remember. And then building on that, though, is that we have kind of a tricky situation with the rule of 3 where we run into some issues with efficiency where we could have a better situation. So like this says, if you guys want, you can type in this link into your browser. It might be a little bit of a pain, so I'll try to put it in chat actually. And then you can hit the fork button and you can play around with this code yourself. Or you can just do what I expect most of you will do, which is just watch me play around with the code. So first question, can you guys see the rep? Like, can you see this code here? Sweet. Thanks, everybody. So first, we're just going to go over this brief class that I've written out here, just basically describing what I just outlined with the class that manages dynamic memory. So we have a constructor. What we're going to do in the constructor, this is basically, we're just going to implement a vector class like we've seen in the STL. So in the constructor, we're going to have some size, capacity, and some data pointer. And we're calling new in the constructor. So this is the important part. We're managing some dynamic memory. And we just have some print statement here so we can see in the demo that's to come what exactly is going to happen. Destructor, we're going to delete the data. This is all not very important. The memory thing is just so we know that we're managing something, and you'll see later why that's important. We have a copy constructor that's going to print out that basically we're copying the data, and you can see that in the copy constructor we're actually doing a deep copy over the data. And then in the copy assignment operator, we are just going to call the copy constructor here. So we're redelegating that work to the function we already wrote, and then we're doing swap. So if you remember from lecture, there's the copy swap idiom where we can essentially reuse the copy constructor to get around duplicating the work of writing both a copy constructor and a copy assignment operator. But the main line here is that both of these things are both doing a deep copy. Yeah, so we've got that. We've got our swap function, which both of those rely on. And then I've implemented a pushback function that if you really want to see, it's down here somewhere. It's basically just doing the push and then grow if you need to kind of idea that we've seen in class, but no big deal. So anyways, with all that said, the important things you need to know at this point is that we have a custom vector class and that I've overridden all of the constructors and destructor to print out when they're called. And I have an ID class or an ID static class member that just tracks, what number vector we've created. So the first vector we create will be vector 1, the second vector we create will be vector 2, and I've labeled the names accordingly as well. So what does the static keyword do here? So good question. I know we don't talk about static members usually like at all in any of the classes here, but static, when referring to a class member, whether that be a function or a data member, just means that this variable is shared amongst all myInt vector objects. So what this allows us to do is, so we have this next ID variable. What we're doing, you'll see down here, I initialize it to 1, and you have to do this outside of the class. If you want, I can talk about that more, but I don't think it's that important. You just have to know you have to initialize it outside of the class. And then what I'm doing is in the constructor, I'm setting each individual object's next ID member to be the shared next ID variable plus 1. So what this is doing in practice, it means that the first time a constructor is called ever in this class, what we're going to do is we're going to set that object's ID variable to be, the class-wide count for how many myInt vector objects there are in existence. Does that make sense? I don't know if that was a too roundabout way or not in-depth enough. Cool. Yeah, so we'll see that when we try to run this in a second. But I guess the main point here is we're just going to try to figure out what the output should be. So thinking about the big three, what we're going to do is create, oh geez, I am losing some lines here. Okay, cool, well that worked. So we're creating a vector, and what I would guess is that this is going to print constructing vector 1. We're going to push back some stuff. I didn't have the pushback function print anything. And then we're going to print it. And I would assume if we implemented this correctly, we're going to get something that looks like 1, 2, 3, 4, 5. So that looks good to me. Then we have vector 2, which is copy constructed from vector 1. And of course, what this should do is do copy ctor, probably from 1 to 2. Then we're going to push back a new item into vector 2. And the important thing to note here is that vector 2 should now have 1, 2, 3, 4, 5, 6. Right? So we want to add that to that, but we want vector 1 to still contain the original data. This is just kind of checking that we're doing a deep copy on our data, and we don't have any, if we did a shallow copy here, both of the pointers refer to the same array, and therefore we would have added 6 to both things. So that's just making sure we're doing a deep copy. And then if we do this, another default constructed myInt vector, we're going to have a ctor 3 printed from this line, and this will call the copy assignment operator. So again, we're going to get another deep copy. So we're going to get copy assign from 1 to 3 will be the output. And then when we print this here, we should also get 1, 2, 3, 4, 5. Whoops. So let's just double check that I'm correct here. I've written a little make file to, let me actually just double check which one I want to use here. Yeah, I've written a little make file to make the construction process a little easier because we've got a bunch of these that we're going to go through. So let's check if we were right. So I said we're going to print ctor1, yep, we constructed object 1. We're printing the first vector, and you can see we have 1, 2, 3, 4, 5. Looks good. Then we're copy constructing from 1 to 2, or from 2 to 1, or sorry, 2 from 1. So yep, what I wrote there is correct. And we can see that this has the 6 at the end. My vector number 2 has the 6 at the end, whereas my vector number 1 does not have the 6 at the end. So we did our deep copy correctly. Then we have our constructing 3, like we said, we're copy assigning 3 from 1. And this right here, this is where it gets a little bit interesting. We see a copy constructing 4 from 1 and then a destructing 4. And this might be a little bit weird just eyeballing it, but if you can remember back to our implementations, we're actually calling the copy constructor in our copy assignment operator, and we're constructing a temporary vector here. So this 4 that's created, this myint vector number 4 that's created is actually this temp vector. And you can see at the end of this function, this temp vector is actually going to go out of scope and destruct. So that's why we get this destructing 4. And this usually isn't that important to worry about. It's just, explaining why the things that were printed. And then at the end, myint vector 3 has 1, 2, 3, 4, 5, like we assumed it would. And we get destructing 3, destructing 2, destructing 1. So all of our local myint vectors destructed as we expected they would. So that's just the brief overview of the rule of 3. Probably at this point, a lot of you are wondering, I already know all this. Why is Michael going over this? And move semantics are actually going to help us in a lot of cases, making these deep copies more efficient. So let's take a look at this second chunk of code here then. So we have this function create big vector, which just takes in a number, and then it just creates a vector with the numbers from 0 to n, or 0 to n minus 1 rather. And then it just returns the vector. So this is pretty straightforward stuff. If we do create big vector with 10, we should expect to see the numbers 0 through 9. And then if vec prints, we should see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But the question here is, what exactly is going to happen with the vector that is kind of temporarily constructed here and then copy assigned to this vector? And a better way to ask this question would maybe be, what happens to big vec, which is local to this function? Are we going to create an entire vector here, which has the items from 0 to 9, and then as soon as it's returned, gets copied into this vector, and then this local variable is destroyed? Or are we going to have a situation where maybe this big vector is constructed, and then all of its data is just now assumed by the name vec? I think a better way to go about this would be maybe to just see exactly what happens and then talk about it, because it's pretty difficult to understand without looking at output, in my opinion. So what we see here is we're constructing 1, and if we follow the code here, actually what this is doing is we're going to go into this create big vector function first. So this is actually vector 1. So we've created this vector, and then before that vector is destroyed, actually, we copy construct 2 from 1. So it's kind of like the in-between of this line here happens before we actually lose the local variable from this function. So we are creating this, which is vector 2 from vector 1, and then vector 1, which was big vec in this function, is destroyed because this function call officially ends. And then we see copy constructing 3 from 2. Let me think about what this is doing. Oh yeah, this is something I forgot actually. But what's actually happening here, so return doesn't finish until the copy construction happens. Yeah, so you can kind of think of the process of a function as being only finished when the return statement finishes. And part of the return statement is kind of storing the return value where it belongs. So part of what I misspoke about there is this is vec1. It's going to be constructed, and at the end of this function, we're going to return it. And we're actually returning it to this kind of temporary variable here. So if we just ignore the left-hand side of this assignment first. So let's say we just had this line of code here. This would still execute and this would still work. This line of code itself, once it's executed, is actually a myInt vector. Once this code is evaluated, right, because the return value of this statement is a myInt vector, the type of this object will be a myInt vector. It's just going to be a temporary, and it's going to destruct as soon as this line finishes. But this in and of itself is a myInt vector. So we have this temporary object here, and that is going to be that's going to be our myInt vector, which is labeled 2. So we already have this kind of temporary thing here, but it has a name. Then we have this temporary thing here, which doesn't have a name. Then what we're doing with this second temporary vector is we're only then assigning it to our actual vector vec. And that's why we have the third vector, which is actually vector vec, which is copy constructed from vector 2. And then we destruct 1 and 2, and at the very end, we get to see 0 through 9 printed, which is the data we expect. And the whole point of this is to just kind of say, if you are copying large data out of a function or out of a piece of code that doesn't need the data anymore. So, for example, this myInt vector big vec variable does not need the data anymore after this function returns. There's no need for us to copy this data, right? We could just steal all the data from this big vec variable and give it to vec. There's no need for us to make a deep copy here. That's just kind of a waste. So that's the idea behind this, and that's the justification for move semantics. I can talk about specifically what's happening with the double copying in 1 second, but I'll answer this question first. Why can't I just create the vector on line 1 and then pass it by reference to the function, no copying necessary? Yep, that's a totally valid way to do this. And I've actually lied to you all a little bit because this isn't how C++ actually works. If you take a look at this line right here where I'm actually doing the compilation step, I have specified a special constructor flag or a special flag for G++. And if I make copy elide, I've specified the same compilation process, but without that flag. And this will make a little bit more sense after I run this. And I'm sure you guys just kind of think about this implicitly at this point. But if I run it without that flag, you'll see that I just have constructing 1 and destructing 1, which is very different from this huge mess of 3 myInt vectors created and 3 myInt vectors destroyed thing we have here. And that's just because of this thing called return value optimization, which I will talk about later. I know this is a lot of information at once, but basically default C++ implementations, compilers are allowed to, specifically for returned values from functions, compilers are allowed to construct the value in place as opposed to constructing it as a local variable. So the default options do this automatically already. Yes, but you'll see there are many cases when the compiler is not smart enough to do this for you. And in order to keep this example, I guess, understandable in a short period of time, I did elect to go with something that was, I don't know, a simpler example. But we'll see in a second. So just to really quick wrap up that last thought, though, this big vector is actually never created if we use the default G++ compilation process. What happens is, instead of creating this myInt vector big vec, what the compiler sees that this function is just returning a myInt vector by value. And because that myInt vector is created in the function and is returned after the function ends, the compiler knows, there's no reason that this vector has to exist at all. Why can't we just create that vector where it's going to end up? Why don't we just create it where the return value is assigned? So that's exactly what happens. Instead of creating a big vec here, you can essentially think of this as, like Thomas said, the function is now essentially taking in this vector by reference, and we're populating the vector itself, right? So vec itself just gets the data. So that's called return value optimization. And if this isn't making sense, I promise this is only like the first slide of this, and it will sink in once we've gone over an example. Okay, But the big idea is without this optimization that the compiler just happens to be smart enough to make, there are a lot of situations where we can get away with stealing the data for temporary objects when they're about to be destructed. So we know a temporary object or an object like this, which is local to a function, it's about to be destructed, and we know it's not going to need its data anymore, so we can just steal its data and not feel bad about it, as opposed to doing a full deep copy. So that's the one thing. Okay, let me answer some questions now. So whoever wrote G++ really thought about every way to optimize code. Yeah, I mean, I'm sure if you really dug deep into the G++ code base, you would find some absolutely nasty lines of code for just some insane optimizations. Are there any encode flags that can explicitly request the compiler to use copy elision? Yes, that's just the default is that, well, specifically for, there are a few cases where compilers are allowed to use copy elision. One of them is return value optimization, which is this example here, where it will construct this myint vector in the returned location as opposed to on the local stack frame and then copy it out. I think there are others, I'm not sure. But one thing that's important to note here is that this copy elision actually does change the outcome of our code. In this case, the only change that we can see is that we're avoiding calling the copy constructor. And you can see, though, there is a difference in output just from our code itself. Our code, the execution of our code changes because of this copy elision. And you can imagine that if our copy constructor did something other than just print something, this could have affected the run of our code. So a lot of cases where the compiler maybe could detect that it could elide a copy constructor, I'm not sure if the standard allows it to in every case, because that changes the outcome of your code, and a lot of programmers probably don't want that. So if that doesn't answer your question, feel free to follow up. But at the same time, there's also a huge depth of knowledge which I don't have about the specifics of compilation. Anyways, let's go back to the slides though real quick, because I think the big idea of this will be coming up soon. The moral of the story, if you didn't get any of that, because we did go a little bit off track, is that if we know the other object won't be using its data anymore, we can just steal it. If somebody has a question, feel free to speak up. Otherwise, I think somebody accidentally unmuted, so just make sure of that before we continue. So yep, other object's not using its data anymore. We can steal it. We don't have any way of doing this with the functions outlined by the rule of 3, though. So if we only have our copy constructor, our copy assignment operator, we can't exactly define like a steal operator. But the main idea here is that stealing the data is often much faster than copying it. So you can think of our deep copy for our myint vector class as being O of n, right? We need to copy each individual data element into our new vector. But our steal operation we could think of as just copying the pointer itself. So if we just take over the pointer itself, and then we give the other object like a dummy pointer, then we know that we now control that other object's data vector or data array, and that other object now controls an empty data array. So stealing is often much faster than copying, and this is exactly what move semantics allow. They allow us to steal the internal data when we determine we don't need to make a copy. So this is the brief aside where we already kind of got into this, but good compilers avoid making the copies without us asking them to in certain cases, such as when we're returning a temporary object from a function. So in our create big vector function before, we already discussed this, but that local variable big vec is never actually created. We just create the vector in the returned spot. And that allows us to avoid making that copy. And it's usually clear that this data that's about to be returned doesn't need its internal data once the function returns, so they can just build it where the value is returned to, never creating the temporary object in the first place. Yep, so maybe some of these slides are going to be me just reading these bullet points and then fielding questions, but I guess that's what you get when you try to make slides that are accessible for people that are just viewing the slides. So let's hop back over to the Replit. Whoops, I guess I can just go here to look at an example where we have a move constructor defined. So let me clear out the terminal. So we have our same myInt vector class, and we have our constructor destructor, copy, copy, blah, blah, blah. And now I've defined a move constructor and a move assignment operator for this class. And the syntax is going to be a little bit wonky here, so I'll go as slow as I can. But if we have, let's just look at our copy constructor first and then compare it. We have no return value, just like any other constructor. And we're taking in exactly one parameter, which is the other myInt vector object that we're copying from. And in this case, we're taking it in by const reference for the copy constructor. And this is typical. You normally take it in by const reference. You could take it in by just normal reference without the const, or I suppose you could just take it in by value. Actually, no, you couldn't, because then that would cause some infinite recursion. Either way, not really important. We're taking it in by reference for copy constructors. And for the move constructor, it kind of looks like we're taking it in by non-const double reference here. And this declaration here is actually denoting that this other value is an R value. And this is a term that probably none of you have ever heard before. And I'm going to have to delay explaining it for a few slides because it would be a huge aside to explain it now. But think of this as the syntax for defining a move constructor. Just looks like that. And then what we're doing in this constructor is we're just shallow swapping with the other vector. So if we look at our swap function here, we're just swapping the first size with the second size, the first capacity with the second capacity, and the first data with the second data. And if we look at our data object or our data member, like I discussed before, it's just the pointer to the int array. So all this is doing a shallow swap. And the move constructor, what it does is just shallow swaps all the members. And that's all it's doing. Man, there we go. It keeps showing like white boxes on my screen for some reason where it's obstructing the code. I don't know if you guys can see that. So just doing a shallow copy there, we're avoiding making a deep copy. And the idea here is if we know that this other vector isn't going to use its data anymore, we just steal it. We can steal it by doing a shallow copy. One other thing to note that's important, which I almost forgot, is that we are actually calling the default constructor first. So before we swap our data with the other vector's data, we are initializing our data with default stuff. So right here, we're initializing it with default stuff. And we're just calling that function to make sure that whatever data we give the other vector after we swap is safe data. So one thing that you might consider is that if we steal another vector's data, what happens when the other vector destructs? Well, we need to make sure that that other vector can destruct safely. And you can imagine that if the other vector was still pointing to the data that we just stole, then when the other vector destructs, it's going to deallocate the data that we wanted to keep. So we need to make sure that we initialize our data vector with something safe, that it's okay for the other vector to destroy when it destructs. But again, we'll see an example of this in a second. I think it'll be important for everybody to take a look at that before we think too deeply about this. And then the move assignment operator, very similar. We're just doing a shallow swap with the other vector, just stealing the data. And then in typical assignment operator fashion, we're just returning the dereference to this pointer. Okay, so what will the output be this time when we do our same line of code? And this time we are going to we're going to use that no allied constructors flag again. So we're going to get every constructor call that you would expect to see here. First question. All right, we got, if we define a normal non-move CTOR to do this, would the compiler yell at us? So this is kind of what we'll kind of get into this in a little bit with the R value talk, but this will only be called when the function signature is matched. So if we're thinking just about traditional function overloads in C++, right, we do have a constructor here where we have myint vector with one parameter, and we have a myint vector with another parameter, or with one parameter here. So these are kind of conflicting definitions, and the compiler needs to choose which one to call in each scenario. And this is only going to be called in very specific situations. So I think, yeah, Paul is right where the parameter is technically different than the parameter for this function here. So they're just called in different scenarios. And I think the bottom line is you can't, well, you could define a constructor that steals the data from the underlying vector object. You would need to know exactly when, you would just need to be sure whenever you called that function that the object could be stolen from. And the advantage of using the R value as the parameter here is that the compiler will be able to detect for us exactly when the other object can be stolen from. So maybe that's roundabout. I promise we'll get to that though in a second. I think kind of the nature with all this is that there's a lot of new topics being introduced at once, and that we kind of just have to work through them. But yeah, this will be useful, more useful than defining, say, a function that's called steal data. And we'll see some explanation for that in a second. So what was the R value again? I'm going to defer that question for a little bit. I know that's annoying to hear, but we'll come back to this code after I explain it. This is just kind of the justification for move semantics. So what's going to happen when we run this new code, right? So we create a big vector. So we're constructing one, which is our big vec here. Then we construct two, which is our temporary vector here, if we remember from last time. And then we move construct two from one. So instead of doing that deep copy, the compiler recognizes that this is a temporary value, and we're constructing this vector here by just stealing this vector's data. And then in the same vein, we're constructing the third vector, which is this actual vector, and we're move constructing 3 from 2 because the compiler is able to recognize that this is a temporary vector. And again, we can just steal its data. So with our nifty move constructor and move assignment operator, we're able to avoid making the unnecessary copies in this case. Okay, and one more thing to note. I guess we'll uncomment that really quick and give it another run. But it's just going to be what you expect. We're going to get full control of the data from this big vector that we created in the function. Why is ampersand ampersand used instead of single ampersand for move semantics? For that, I think it's just they needed a way to differentiate the R value reference from an L value reference in the standards committee. And again, we're just going to, that'll be something I'll defer for another slide or two. Okay, so this little note here, maybe this is getting in too deep, but I think it's important to note. So if we steal the other data, and remember when we steal the other guy's data, we're just giving them whatever our data was. And if we don't, say we don't default initialize ourselves when we run this code, what's going to happen is, if I can get there, we're going to have this weird double free or this core dump here. And the basic explanation for that is that when we move constructed the data out of this function, we moved it to this vector here, but this vector here still has to destruct. So when this vector destructs, and you can see it here from the destructing one call, we didn't give it anything else to point at. All we did is we swapped the values that this was initialized with its other data. And this wasn't, we don't really have any data in this case. We didn't initialize any of our member variables to anything. These are all uninitialized, and we gave the other vector totally uninitialized data. So it's not valid for the other vector to delete uninitialized data, because probably this pointer is not null pointer, which means it's not a safe thing to delete. And as a result, we get some invalid free and we get a core dump. So that's just why it's important to initialize your own data before you swap it with somebody else that you're stealing from. Okay, so let's hop back over to the slides, and I'm sure I will answer a million of the other questions that have popped up in chat. So return value optimization is one instance where the C++ standards allows compilers to align the constructors. So we had matching function calls in our myint vector class. In this case, or in the previous case, we had copy constructors that matched. But the compiler determined we didn't need to make a copy there, so instead it built the object in place. So this is just a big aside about how, like I said earlier, if we actually were relying on the side effects of that copy constructor being called, then maybe this would be a bad thing. But usually it's a good thing. So I'm going to skip over that because it's such an edge case. Here we go. Let's get to L values and R values, and then I'll answer the chat questions. So in C++, there is a, not in C++, in most programming languages, there is a distinction between R values and L values. And I think let's just talk about this a little bit before we, I guess, get too much into the theory. But definition of an L value you can think of as being something that can be on the left-hand side of an assignment. So if you want a little mnemonic, you can think of it as a location value. Cute little L there at the front, is it only represents the location of some data. Variables, which are names that refer to data, are L values, whereas the definition of an R value is that something that can be on the right-hand side of an assignment. A good rule of thumb is that these are read-only values. Temporary unnamed variables are R values. So, whoops. Let's just go through this code here, and I can point out what are R values, what are L values, and hopefully that'll give you some idea of what these words mean. So, first thing I'm noting here is right hand of this assignment is the string literal apple, and the string literal apple is an R value. It doesn't have a name or variable associated with it. It is just data. The good rule of thumb, I think, is important here. It's a read-only value. If we try to assign something to the string literal apple, nothing would happen. That's definitely not valid. You can't store something in a temporary object. Right, so this string literal apple, it's an R value. Banana is an R value. Orange is an R value. The S1 name itself, though, is an L value. Right, so it's a variable. It's a location where we can store data, and ultimately it's just a name that refers to some data. So whereas R values are usually just raw data, the L values are usually names that refer to raw data. So S1's an L value, S2's an L value, S3's an L value. Whoops, I keep scrolling on accident. Vec1, L value, just another variable like we talked about. Here, more examples. X and Y are L values, but the 3 and the 4 are data themselves. They're R values. Here's another, I think, canonical expression here. We have an assignment where we're assigning to an L value, right? But the right-hand side is an expression. So what's happening here is S1 plus S2, what that's going to evaluate to, it's going to evaluate to some new string object. The new string object is going to contain the text apple banana, but that's not going to be stored in any variable yet. It's just a temporary variable or a temporary value that contains the string apple banana. And then that temporary value is going to be stored in the string S3 variable. So the expression itself, S1 plus S2, is an R value, but S1 itself is an L value, and S2 itself is an L value. And then there are some other examples down here. But at this point, if anybody wants to pipe up and ask any questions about this or put anything in the chat, I recognize that this is a pretty difficult concept to grasp on the first time around. So if anybody wants to ask any questions, please go ahead. I guess from chat, if we weren't using copy swap, we would only construct 2 vectors here, correct? Let me see. So if we go back to our example, all right, let's find out. I think if we weren't using copy swap, we'd only construct 2 vectors here. I think you're referring to the temporary vector here, or not temporary, the local vector here to this function, and then the like true temporary vector here. No, we would definitely still have both of these vectors. Yeah, we would still have both of these vectors, and if you see the move if we go back to our copy, I think is the better example. If we go back to our copy constructor example, you can see that it's actually calling the copy constructor, not the copy assignment operator. So even though it looks like we're doing an assignment here, right, it's actually calling the copy constructor. And that's just something that another G++ thing, most compilers will make this optimization where if it detects that we're creating a new variable, usually it will call the copy constructor instead of copy assignment operator. So if we had the copy assignment operator, I agree we would have a temp vector constructed and then we would swap with that temp vector. But in this case, it's actually calling the copy constructor, which doesn't create another local variable. So that's just another icky compiler thing that it just does without your knowledge. And now I've lost the chat. Okay, chat, back here. Okay, informal answer, just to help understand. R value is value without a member location, something that can only be used in the RHF on assignment. Yep, very good from Paul. Great explanation. Okay, Alan asks, how does ++x and ++x do to R or L value? Any specific use cases for either? Yeah, that's a great question. So let's hop back into this. So this was a specific funny edge case that I remember looking up myself because I didn't remember when I was writing these slides. So what x++ is actually doing is it is incrementing the value of x, but the expression itself evaluates to the old value of x. So, for example, I guess let me again hop back over to the code here. So let's say we have int x equals 4, and then we see out x++, right? What we're going to get is, make sure I'm actually right about this. Right, we're going to get 4. So x is actually incremented, but we're going to get the old value of x as the result of this expression. And then if we see out x itself, you'll see that we end up getting 5 because it is incremented, but we get the old value upon return. So the consequence of this is that x++, it can't return the value itself because the value itself needs to be updated and we want to return the old value. It has to return a temporary copied value. So if we think of, man, this would be nice to have something I could draw on here. But if we think of like x is being stored up here, just like using my hands as a diagram, if we want to assign a value to x, then we need to actually know this location here. We need to give whatever, I guess, assignment that we want to use. We need to give it this location here and say, hey, put whatever value you want to assign in this box. But because we want the old value of x to be returned from the expression x++, what happens is we need to increment whatever's in this box here but we want to return the old value. So we can't return this box here. We have to return a temporary object that has the old value. So as a result, say we wanted to do something like this, you'll see that it's going to yell at us for this being not assignable. And what that means is that x++ is evaluating to an R value, or something that cannot appear on the left-hand side of an assignment. Conversely, though, or not conversely, maybe somebody who just took 203 can help me out with what I mean by that. If we do ++x here, I guess this is probably a better way to do it. ++x, because ++x prefix actually increments the value before the expression returns, and this evaluates to the incremented value. We can actually just return from this expression that box itself. So if we do ++x, we're going to have the old value, say the old value is 4. It's going to be incremented to 5, and then that whole expression itself can actually evaluate to the object itself. It doesn't need to evaluate to a temporary object. So as a result, we can do ++x and then assign that a new value, because ++x is an L value, whereas x++ is an R value. So that is probably overkill for what you're asking, but hopefully that makes sense. Let me know if that didn't make sense, and I can go in a little more depth about that. So, but how many of these R values actually exist when the preprocessor gets around to optimization? Good question. I think I'm going to defer that a little bit, because you don't need the processor to, or you don't need the preprocessor or the compiler to determine what is an L value and what's an R value. You can actually specify it yourself and say, hey, I know better. In this case, this is actually something that's going to be used. So is x equals 3 the same thing as plus x equals 3? Yeah, I mean, in the case of just having integers, of course, incrementing the value of x beforehand has no effect on it. But yeah, I think what you're getting at is that plus x equals 3 does change the value of x. Yes, it changes it to 3 specifically. By the end of the line, plus x equals 3, x will have the value 3, no matter what happens. Yeah, and that actually, if you want all that, if you want to see all that code golfed, pointer arithmetic stuff, then I agree this is pretty important stuff. So that's kind of the distinction between L values and R values. Feel free to keep asking questions if you want. But now we have our full rule of 5, which is the updated version of the rule of 3, where if you have a copy constructor, copy assignment operator, we probably also want to define a move constructor and a move assignment operator along with the destructor. And that's just because if we have some resource that's being managed by our class that, it's a sufficient resource enough to where we need to specify rules for how it is deep copied, then we probably also want to specify rules for how we can steal that data. And that's just the basic idea there. So let's take a look at our previous example using that. Interesting. Well, I think I already did that, so I'm not quite sure why I put this slide in there twice. Okay, so now we have I think what Thomas was asking about earlier, but std_move is a function that allows you to tell the compiler that, hey, the object that I'm referring to is actually an R value. So from CBB reference, this is just exactly what CBB reference says. std_move is used to indicate that an object T may be moved from, i.e. allowing the efficient transfer of resources from T to another object. It is exactly equivalent to a static cast to an R value reference type. So in other words, we're just telling the compiler to interpret this value, which likely has a name in this context, and thus is an L value, as an R value reference. Okay. So I think getting at Thomas's question earlier for why would this actually matter, why would you ever need to do this, because the compiler is probably going to take care of all those cases for you. And the answer is that you can tell the compiler, hey, in this case, we need to treat this value as a value that can be moved from, or a temporary value that we can steal from. So here's an example of using std_move. let's say we have two functions of foo up here. We have one that takes in an R value reference myint vector, and we have one that takes in a const L value reference myint vector. So we construct some vector here, and we call foo on std move of v. So which version is called? If somebody wants to take a shot at answering, go ahead. Top. I agree. Perfect. And this is just because even though v, in the context of main, v is an L value. V has a name. It can be assigned to, it is an object that refers to the location of some data, or it's a name that refers to the location of some data. It's an L value. But what happens here is that we're calling std move, which is basically telling the compiler, hey, treat this as an R value reference. So as a result, we are getting version A of that function call. But down here, we're going to get version B because v is an L value. So thus, we're getting a const myint vector reference vec, which is just a const L value reference. Cool. And then this is the kind of the kicker here with using standard move or std move is that what if this version A of the function steals our data? And this is kind of the point of having functions that take in R value references, is that we're telling the function that, hey, this vector doesn't actually need its data anymore. You know, you can steal from it. So it's totally valid for this function to just take the data or modify it in any way that you want, because we've told this function, if we're in this function at all, this function should expect that vec is data that can be stolen freely. So if foo steals our data, then we don't know what's going to happen in this call down here, the second call of foo. You know, the state of v is completely undefined after this call, unless we knew exactly what this first function call was doing in the definition. But yeah, you can't really rely on the state of an object after it's been moved. So that's just saying that foo may or may not steal our data or change it or do anything to it because we've told it, go ahead and do it. So if we go back to our move assignment operator, remember, all we did is we just swapped the data in the current vector with the other vector's data. And if we imagine the same thing happening here in the definition of foo, maybe we got some other vector's data just randomly. Maybe we got like 4, 5, 6, 7 is the new value of myint vector v. And that's just something where, again, you don't know what to expect if you are using move on some value that you want to use later. So rule of thumb, only use std move when you don't actually need the value of the variable after it's done returning. So just another thing to point that out there. And then I guess let's go back to that really quick, and I'll try to answer some of these questions. If anybody has any questions about std move, feel free to put those in there. Now understand 30 seconds of lecture where Dr. P said we need the rule of 5 without explaining what the other two were. Yep. Some more pointer stuff, some Piazza stuff. Cool. Okay, yeah. If anybody's got any questions about std move, feel free. Does std move just say make this an R value? Yep, that is all it does. And in fact, if you go to the CPP reference page, it is exactly equivalent to a static cast to an R value reference type. And that is just true. It's a friendly way to just do an ugly static cast. Yeah, which is pretty funny, but a lot of the times it's very necessary. So that would be static cast, myint vector, ampersand, ampersand, v. Yes. Yep. And in fact, if you want to avoid using std move and you just want to do the static cast yourself, that's totally valid. You can cast all your L values you want to R values the long way, and that's totally valid. Okay, I'm going to try to pick this up because even though move semantics are probably the hardest thing in this mini lab, then they're not the only thing. So let's keep going. Okay, so we've already got that. We've got universal references. I'm going to breeze over this very, very quickly. Feel free to ask questions, but this is kind of a dark corner of C++ thing. which is not used. I have never used this personally, but I can imagine others using it. So if we want to template a function to take in both L value and R value references while still preserving what type of value they were, then we can do this with something called universal references. So feel free to read the rest of the slide, but let's say we have this function bar, and based on the type of the vector that's passed to it, we want to call the appropriate version of foo. And the question is, do we have a way to do this? Or do we need to have a version of bar that takes in, an R value reference and a version of bar that takes in a const L value reference and duplicate that code? And the answer is yes, there's a way to do this with something called universal references. So this is, I would say, some undeniably ugly code, but I'll explain what it does very briefly. We've got our two versions, R value reference, const L value reference. We have the function bar here that was previously mentioned. It is templated, and the type of the parameter is T ampersand ampersand. And this is controversially, or maybe not controversially, called a universal reference as opposed to an R value reference in this context. And I guess without going too much into it, if we look at this code down here, if we call bar with an L value, what's going to happen is this vec is going to be initialized with a const L value reference. And then when we call this stood forward, which also needs to be templated, it is going to forward the underlying value of vec. So you can think of vec as knowing what the original type of the value was upon passing. So in the context of this function, vec has a name. So vec is always going to be an L value. But when vec was passed to this function, it actually might have been an R value. So in this case here, my int vector is a temporary value. So when we pass this to the function bar, vec was originally initialized with an R value reference. But again, in the context of this function, vec has a name, so thus it is an L value. So if we want to get back that R value reference that we had when we passed the value to this function, we need to call stood forward, which more or less you can think of as achieving or accessing that previous true type of whatever vec was. And it'll call the correct function as a result. So these both call bar first, but this one is going to call version B of foo, which is the const L value reference. And then this one's going to call version A of foo, which is the R value reference. Again, not really that important. I'm going to skip over that. Quiz time, I'm also going to skip over this. Feel free to go through and check out quiz.cpp. It's just a lot of examples with a bunch of this stuff being exercised and just picking which function will be called in each of the given instances. This is tough stuff, so do not worry if you're not getting it just from this. And we clearly do not have enough time to even go in depth at a high level about this. So I think we're going to skip ahead to smart pointers, but first I'm going to answer all the other questions in chat that I see. So does the compiler optimize by automatically R-value casting variables the very last time they can be used? So that's a good question, and my answer is I don't know, but from my experience, the answer is no, because that's actually a very difficult, that's often a very difficult question to answer. You can think of the easy example where if you have a local variable declared in some scope, say that's about to destruct, it's very easy to tell, hey, this value will not be used after the scope destructs. Therefore, you can steal its data right now. But it's not very easy if the variable is outside of some scope that's about to destruct. And I think oftentimes you cannot tell that. And if you want to mark that an object is stealable, then you need to do it explicitly in a lot of cases. And also for code readability, you should use stdmove if you want to indicate that something should be stolen, even if you know the compiler is going to do it on its own. That said, You don't need to std move clear temporary variables, like in our last example where we have, my int vector passed as just a default constructed. Clearly, there's no name. Clearly, this is temporary. You don't need to std move that. Cool. Hopefully that answers your question. With that said, I'm going to move on to smart pointers because we don't have all night to do this stuff. But hopefully that's a good overview. So, totally shifting gears here. You probably remember from EECS 280 that managing dynamically allocated memory is hard. You saw a lot of that in what we just talked about here. A lot of issues, dangling pointers, double freeze, memory leaks, all that good stuff. And there is a special class of objects that you can use in C++ and in a lot of other languages to completely avoid ever using the new or delete keywords. And I think these are completely fascinating, and I would expect, I haven't seen a lot of C++ production code, but I would expect these are all over any piece of complicated C++ code because they simplify things a lot and they have very low overhead in C++ fashion. So the basic idea is we have a class that takes in an object and it deletes the object when it detects the object is no longer being used. So it's a pretty simple idea on paper. You can think of it as our constructor in our myIntVector class, which calls new in the constructor and it calls delete in the destructor. You can think of it as being very similar to that, but maybe we don't call new in the constructor. Somebody gives us something they want us to allocate, and we manage and delete it when we detect it's no longer used. So Akshay asks, does Java do this automatically? So Java uses garbage collection, which is not exactly the same implementation-wise as smart pointers in C++. I believe Java uses the Shenandoah garbage collector, which I think is a lot more complicated than C++ smart pointers are, and that it's probably a lot more efficient at detecting things that aren't being used. And it'll be able to detect usage cycles and stuff like that, I believe. How does this differ from garbage collection? This differs from garbage collection because garbage collection is often... That's a tough question to answer because garbage collection is kind of a background process that runs underneath garbage collected languages, whereas C++ smart pointers are kind of a programmer implemented thing where we are actively managing the memory and we're choosing to do it in a certain way as opposed to calling new and delete. Yeah, I don't think I have the knowledge to give a much better answer than that, but they're definitely different. They're definitely different things, but very similar idea. Yeah. So let's move on, though. So the first class that we're going to look at is called std unique pointer. The goal is we want an object to be managed by a single pointer. And if we have a class that takes in a pointer and in that class's destructor, we call delete on it, then we kind of get that functionality. So let's just move ahead to an example. I think that'll be the best way to go about this. So let's say we have some item. This is just a general struct in our constructor. We have some int variable. We create some item, and then we have a destructor that destroys it. And we have a vector of unique pointer of items. So you can essentially think of this as being equivalent to a vector of item star of items. But we're using the smarter C++ version of memory management here. So just as a justification for using dynamic memory at all, instead of adding some items to this container in our main function, we're going to add them in some other function. So we're going to add 10 items to our items container, and in our add items container or add items function, you can see we're just going from 0 to n, and we're pushing back a unique pointer of item with the new item constructor I. So we are giving this unique pointer object control of the pointer returned by the new operator here. We have the address of some item object, and we're giving std unique pointer control of that that underlying pointer. So that's kind of the justification for what's happening there. And at the end of that line of code, items is going to have an item with value 0 through 9. So it's going to have 10 unique pointers in it. Pretty straightforward stuff there. Then for each of these, for I guess 5 of these items, we're gonna process them. So we are going to just pop the back of the container is all that's going to do. And then at the end of that, we're going to say done processing. So the idea, I guess let's just look at the output. So 10 items are created at first in this add items function. Pretty straightforward. And then when we process each item, you can see that we're getting destructors called here. Remember, our destructor prints item x destroyed. So every time an item is processed, that item is actually destroyed. And that's because when items.popback finishes, the unique pointer is going out of scope. So items, yeah, the only place that this item object is stored, or more accurately, this unique pointer is stored is in this container. So when the unique pointer itself is removed from the container, the unique pointer destructor is called. And in the unique pointer destructor, it's going to call delete on the pointer it was given. So when we pop back on the items container, the item object itself ends up getting deleted. And that's the, I guess, magic of unique pointers there. So when we call process item 5 times, we get 1, 2, 3, 4, 5 items destroyed. And then it's done processing. And after main ends up returning, our file scope variables are going to get destructed. So the items vector is going to get destructed, and we'll see that the rest of our unique pointers are going to get destructed and thus clean up their associated item objects. Cool. So a few more questions. Andrew asks, did they use RAII stuff to do reference counting, like incrementing some counter on copies and decrementing them when the local references go out of scope? Yes, and we will see, I will go in depth on the implementation of these because I think it helps a lot. But if you're talking about garbage collection stuff, then the answer is, yeah, a lot of them do use reference counting, but they don't have to. Yeah, Gabe with the link to what Java uses for garbage collection, that's fantastic. Why don't pointers automatically delete whatever they're pointing to when they go out of scope? So the justification for why that's not the default behavior is that it's just slower. That's another good point, Ian, is that weak pointer does that, and I'll talk about that in a second too. But even if we have a one-line destructor that calls delete on some pointer, or if we have something else in our destructor, even though it's only one line or something, those lines of codes for performant applications may not be necessary, and they may just be wasting time. So I think the justification when C++ was created was to maintain the efficiency of C, and they determined that although smart pointers were, I guess, a popular thing in the community, it wasn't something that should be the default behavior. Yeah, and if you have, if everything uses smart pointers as somebody, you may have double free if I think you delete every pointer. Yeah, so you can't delete, or you don't want to delete pointers that are referred to by smart pointers because they're already managing the object for you. Cool. So I think some other questions are going to be answered in a second here when I get into the implementation of shared pointers. So unique pointer was very simple in that it just takes control of one object and it deallocates it in the destructor. And this is useful, but sometimes we want to have more than one pointer that's referring to an object. And unique pointer, you can think about if we have 2 pointers pointing to the same object and one of them goes out of scope, then the object's going to get cleaned up and our second pointer is going to be pointing to nothing. We're going to have a dangling pointer. So the solution for this is that there's a second class of smart pointers called shared pointer. And they allow any number of objects to, or any number of pointers to refer to the same object. And instead of just having a simple constructor and destructor, we have a manager object that knows how many pointers are referring to the given object at any time. And only when 0 pointers are now referencing the manager object, it can free the memory for the underlying, I guess in our previous example, it was an item object. Yeah, and in my opinion, these are much more useful than unique pointers. And I had a project for EX381, which is a class that is unfortunately not being offered anymore. But you can just replace any instance of a raw pointer being used with a shared pointer, with a few exceptions, and your program should behave exactly the same. Because they should have the same syntax and the same, I guess, the same effects as using normal raw pointers if you replace them just word for word. They're also copyable and movable, copyable and movable. Just some more helpful stuff to know. So let's look at an example. Let's say we have our shared pointer container of items instead of our unique pointer container of items. So we've changed some definitions here a little bit. Let's say we just add the container or add the items to the container in line here. One thing to note is that we have this locally stored shared pointer to item number 0. We're putting that in the container, so items just has 0 right now. Then we're adding item 1 through 4. Then what we have is, oh yeah, I remember this was kind of ugly, but the idea is that we're processing the back 4 items of the container here. Yeah, and then we're done there, and we can see the effects of that. So console output, 0 through 3 created. So that's 0 created here, and then up through 3 created in this loop here. Then we get a new line. We are processing item 3. So what we're going to do is we're going to process the item, and we can see that items.back, which is a shared pointer, is copied into this temporary shared pointer item object. Then we're popping the back of it, and we're returning the temp variable, which is still referring to the shared pointer that used to be at the back of the container. So if we were using unique pointers, when we called pop back here, this temp pointer would actually be pointing to nothing because it would have destructed that object. But because we're using shared pointers, the pointer that's returned from process item is still referring to the object itself. So item returned X is still alive, and we can see that item 3 is still alive. And then only once this returned object goes out of scope, and thus there's no more reference in the container, and there's no more reference in this local scope here, only then is the object destroyed. And we can see the same thing for item 2 and item 1. Item 0, however, is a special case because even though we had the copy of item 0 in the items container, and we had the copy of item 0 in this local variable for loop here, we also have the, unfortunately I named it local, but we have this variable here at the top of main that's also referring to that same item 0 object. So the item 0 doesn't get destructed when we run through the scope here because there's still something referring to it. Then after it's done processing, we can see that local item still has the value of 0, so we're still able to access it. It didn't get destroyed, just like we talked about. And then only after this, the main function exits does that final reference go out of scope, and we can determine that the object's no longer being used, so it gets deallocated. So another question, if I declare 2 unique pointers to the same object, you get a double free, but using shared pointers, you would be fine. Yep, and that's kind of the whole point. And in fact, this is the whole reasoning behind this next slide here, which if you try to view it on your own, it will look terrible, but that's because it has a lot of animations, which are going to help with this. So we have same class as our last example. We have our item class. Say we're creating a new item and we have a shared pointer that refers to it. Here's what's going to happen. First thing that's going to happen, we're going to create a manager object. So the manager object is not the item object itself, and it's not the shared pointer object itself. It is something else. It is an object created by the shared pointer class to manage your item for you. So the manager object is going to create the item itself, and it's going to keep a raw pointer to it. And then whenever we have a shared pointer that refers to the object, it's actually going to refer to the manager object. And the manager object is going to intelligently keep track of how many references there are to it. And because we've defined the shared pointer class ourselves, or because the C++ standard library defined it themselves, that's something that can be easily done. You can easily keep track of how many times shared pointer copy constructors are called, how many times shared pointer constructors are called. Very simple stuff. So right now we can see we have one reference to our manager object. So just pointer one, the only reference there. Pretty straightforward. Now let's say we have pointer two, which is copy constructor from pointer one. How does this change what we're looking at? Well, we just have another thing that's referring to the manager object, and we can see that we now have two references instead of one. And oh yes, this is a big point here, is that even though we're pointing to the manager object ourselves and we're not actually pointing to the item object, the dereference and the error operators are defined to give you the raw pointer versions of those operators, which is very convenient. It would be very annoying to do dereference pointer one, arrow raw, instead of just dereference pointer one. So yeah, I think that's a huge selling point of using shared pointers. So we do another thing. Let's say we do copy assignment this time. We just have another pointer that refers to the manager object. Now we have three references. So now let's say pointer two goes out of scope. We have references are now just two, because in our destructor we could tell that the managed, or in the destructor of the shared pointer, the reference count was decremented. My goodness. Then if pointer one goes out of scope, you'll see it happens again. Then pointer three is going to go out of scope. And once this count hits 0, we know that there's no way for anybody to access this object ever again. Because if we have no reference to it now, we have no way to create a new reference to this. So we are free and clear to clean up the data. So what's going to happen is the object itself is going to get cleaned up, and then the manager object is going to get cleaned up. So that is a just drawing example of how shared pointers are implemented. Any questions for that? Is there an in-place equivalent for making, let me get some pointers back up here. Is there an in-place equivalent for making a shared pointer, like how you can use in-place back on a vector and pass in params for the items tutorial? That is a fantastic question. Yes, there is, and it will get rid of this ugly new that we see here. It's called make shared, and I will talk about it in like 2 slides. It's fantastic. Okay, so any problems with shared pointers? I guess before that, we'll talk about this. Another question, how much overhead actually is there with using shared pointers over manual management? So I guess my answer would be it's not that much. You have just off the top of your head, and this is, to be clear, this previous example that I showed, it's not defined by the standard how smart pointers have to be implemented. This is just the way that I was taught that smart pointers are implemented. But a compiler, any given compiler, is free to implement it however they wish, so long as it, achieves the same functionality. But in this example, if this was how smart pointers were implemented, we would just have one more new allocation for the first time an object is allocated. So we have new item 5 here. We would not only create the item object, but we would also have to create the manager object. So that's something that's, it's one more new call that might be, something that you want to make a note of. And at the same time, in every copy constructor, move constructor, basically in every one of the big 5, you're going to have to do some kind of work on the reference count here. So for shared pointer, I mean, in the copy constructor, you're going to have to increment the ref count. In the default, not the default constructor, in the normal constructor, which takes in the raw pointer, you're going to have to increment the ref count. In the destructor, you're going to need to decrement the ref count and potentially clean everything up. So although it's basically you're just going to need to do some pointer increments and decrements here and there, and you're going to do one extra allocation at the beginning. But I would say it is a cost that is not that much. It's not that high a cost to pay, and most, I think, production level programs would prefer to use smart pointers over raw pointers because raw pointer bugs are nasty. Hopefully that answered the question. Okay, so another example where we have potential problems is that if we have, let's say this person class, which has a shared pointer referring to, let's say, the best friend. And then in main, we say we have some people objects here, which, oh yeah, so this is make shared, and we'll talk about this in a second. But we have person object Albie, we have person object Jade, person object Nikhil, person object Mina, and let's say we set their smart pointers, or we set their shared pointer for best friend to, you know, some other person in that group. The question is there a problem here? So this is probably a tough question to answer, but does anybody see a problem with the setup we have outlined here? Rip Nikhil. Oh, because nobody set him as the best friend. Yes, I think Gabe hit the nail on the head. In that we have what are called circular references here. So if we remember our definition of shared pointer that we, I guess, created earlier, we only destruct objects when they have no shared pointers referring to them. So even when Albie, Jade, Nikhil, and Mina go out of scope, we're still going to have the internal shared pointers referring to them. So they may or may not have other people or other smart pointers still referring to their person objects. That is a terrible way of wording it, so I'm glad that I drew a picture to demonstrate exactly what I'm talking about. So here is the picture that we can that we have from the given code from main. So we have our pointers, which are referring our local variable pointers in main, which refer to each of these objects, and then we have the shared pointers themselves, which are referring to the objects, but from within other person objects. So of course, Nikhil's shared pointer refers to Mina, Mina's refers to Albie, yada yada yada. So when we leave main, we can think of these pointers as destructing. And again, because we don't allocate these person objects in main, these person objects themselves aren't going to destruct. We only have the shared pointers, which are going to destruct. So the pointers go away. The reference counts all get decremented by 1. But you can see that none of the reference counts, well, Nikhil's reference count is 0. So he ends up getting destructed, which not a great thing to just say. Mina ends up getting destructed because Nikhil's pointer is no longer referring to Mina. And then we have the problem here where Albie and Jade are referring to each other, and there's nothing else we can do. They're never going to get destructed because they each still have one pointer referring to them. So this, as Gabe mentioned in chat, we have a cycle of shared pointers, which means that the ref counts are never going to hit 0. The manager objects are never going to invoke their destructors, and these two person objects are going to be leaked. And this is a memory leak, and you can imagine how in a larger application, if you were to maybe run something for a long amount of time, this could be a problem where you'd end up using way, way, way more memory than you need to. So the problem with the previous example is that we don't really want the best friend pointers to have ownership over the person objects they point to. So my rationale in English language for this is if the person no longer exists, the idea of somebody being their best friend shouldn't really keep that object around anymore. We should more accurately say that like their best friend, is no longer in scope. Maybe it's a little bit morbid to use person example there, but let's ignore that for the time being. So standard weak pointer or std weak pointer, as somebody mentioned in chat, solves this problem. Weak pointers don't contribute to the ref count. So they don't keep the object alive, but they can tell you when the object has been destructed. Smartly leaving off the word destructed there from that sentence. So whenever we don't want to assume ownership of an object, we use weak pointer instead of shared pointer. And of course, this is usually only relevant in cyclical reference cases, but there are maybe other examples for when you want to use them. So back to our diagram. I've ignored the first few animations because they were a pain to do. But if we have shared pointers and weak pointers, we can see we no longer just have one ref count. We actually have a strong reference count and a weak reference count. So 2 strong references or 2 shared references, 1 weak reference. And we'll see what happens when everything goes out of scope here. So S pointer goes out of scope. We now only have 1 strong reference. S pointer 2 goes out of scope. We have 0 references. And when we have 0 references, same as before, the item object itself, or the raw pointed to object itself, actually is still destroyed. So what that means is if we try to access the object through the weak pointer, we are not going to be able to. And this is good. This is exactly what we wanted, because in our previous example, this would mean that Albie and Mina would destruct, or Albie and Jade. So now if the weak pointer goes out of scope, the manager object is going to destruct. But it's important to note that it did not destruct before the weak pointer went out of scope. So when we still had a weak pointer referring to the manager object, we could still tell that there wasn't anything pointed to by the raw pointer. So we could tell that the object has been destroyed, and that's important. You're going to find out when we use it later. So that's the gist there. If we have no references at all, we clean up the manager object. But as soon as we have 0 strong references, we clean up the managed object. Cool. So if we go back to our previous example, let's say our weak pointers are dotted lines, and our strong pointers or shared pointers are the bolded lines. So we leave main, and another note from, I guess, EECS 280 here is that the destruction happens in the reverse order of the construction. So Mina was constructed last, so she will be destructed first. So her pointer, oh yes, and you can just assign shared pointers to weak pointers. They are implicitly convertible like that. Doesn't that mean that the manager, doesn't that mean that the manager objects would leak in the previous example? Yes. Yep. So not only would the person objects in the previous example leak, the manager objects would as well. And that's something that I didn't draw on the diagram because that would require 4 more boxes, which would be a little bit annoying. Are we going through all the topics today, or are we stopping at smart pointers? I'm planning on going through all the topics, and I think after smart pointers, they get significantly easier. So I will pick it up, but I don't plan on taking up, more than maybe 3 hours. So if it goes beyond that, then I'll probably leave it. Anyways, continuing, Mina pointer goes out of scope. So no more shared pointers referring to Mina. So Mina, the person object, will go out of scope. And thus, Nikhil's weak pointer will be able to detect that there is nothing there anymore. And we'll see later how that's relevant. Then Nikhil's shared pointer goes out of scope. So the Nikhil person object is cleaned up. Then, Jade goes out of scope. We can see that even though there's a weak pointer referring to her, that does not affect that the person object is cleaned up. And then similarly, Albie goes when there's nothing referring to him. Cool. So last few notes, you can use them pretty much like you can shared pointers, except for you can't actually access the referenced item with a weak pointer. You must create a shared pointer from the weak pointer to access it. And weak pointer lock is the function you want to use to do this. If you have a weak pointer and you call lock on it, it will return a shared pointer to the managed object if the object still exists. But if the object doesn't exist anymore, then you'll get a null pointer, which is very useful if you want to determine, if the object still exists or not. And if we were using raw pointers, obviously there's no data under the hood for a raw pointer, so it has no idea of knowing if the thing it's pointing to has already been cleaned up or not. Another question from chat: why doesn't delete automatically set pointers to null? Would be super convenient. I agree, and the answer is just that. Again, that's one more slight annoyance for maybe folks that want extremely performant code, because even though it's only one line, it is an assignment that is technically unnecessary. So I'm sure a lot of folks writing extremely performant code don't need that extra line of code in there. Yeah. So real quick usage here. Let's say we have a weak pointer. This is just directly from CPP reference, by the way, this example. So what we're doing is we have, I skipped over the explanation here, but we're making a shared pointer to an integer, and we're referring to it through a shared pointer. Then we're making a weak pointer, and we're calling observe. So in the observe function, we can see the use count, which is just getting that reference count that we looked at earlier in the manager object example. So we're going to see use count. I believe it's just going to say 1, because I don't think that takes into account weak references. And again, we're going to use a shared pointer to refer to the actual object itself. So we're going to call the lock function to get a shared pointer. And this is another cute little thing, that the left-hand side of an assignment is actually what the assignment evaluates to. So if gw.lock is a null pointer, then this whole assignment, which evaluates to SPT, which is a shared pointer, SPT will be a null pointer, which means that the entire expression will evaluate to null pointer, which in the context of a conditional evaluates to the Boolean false. So this is actually the same thing as saying auto SPT equals gw.lock, and then if SPT is not a null pointer, do the following. Pretty cute little thing. And then my favorite thing in all of C++, which is you can actually do, you can kind of do two expressions in an if statement, I believe as of C++ 14. I could be wrong about that. But you can do an assignment, or just some pre-expression, some pre-assignment to the if, and then you can specify a second Boolean condition afterwards, and that will determine, the second condition will actually determine whether or not the if is taken or not. And better yet, this is totally unnecessary to know, but this SPT object will be destructed after the if and any coming else's. So totally irrelevant to know. Anyways, so console output, use count is 1 the first time we call observe. So that makes sense. We have one shared pointer referring to it, and we can dereference it once we get the shared pointer. We can see 42. Then after this inner scope in main, the shared pointer goes out of scope. So the object, the 42 object itself, is destroyed. And the second time we call observe, you can see that we have 0 use count. And when we do this conditional, the manager object tells us, hey, that object doesn't exist anymore. So we say GW is expired. Cool. I am going to skip this, but the gist of it is, don't mix regular pointers with smart pointers. If you're using smart pointers, typically you just want to use smart pointers. As a fun exercise, try to think of some bugs for how you could come up with that. And this is the brief explanation of make shared and make unique. Is instead of using naked news for the argument to a shared pointer constructor, instead what you can do is you can construct a pointer from this make shared function call, which is also annoyingly templated, but you just need to give it the arguments to the constructor, and it will create the shared pointer for you. And it will first, I guess the make shared call will create the item object itself, and then the shared pointer constructor will create the manager object, and you'll have all of your memory management set up for you without having to call new or delete explicitly anywhere in your code. So this bottom line of code is typically how you would see shared pointers declared and used in code. All right, so skipping ahead a little further, RAII, I'm going to touch on this super briefly, but the idea is for any resource in general, we can use C++'s guarantee, and other languages have this guarantee too, but C++ has a guarantee that anytime objects are constructed in a scope, just before they go out of scope, their destructors will be inserted in the reverse order in which they were initialized. And the main part is that destructors will always be called when an object goes out of scope, and they will always be called right at that exact point. And we can use that to do some pretty nifty things. And this idea is called RAII, where in a constructor, we acquire some resource. In the destructor, we free up that resource. And it's a pretty nifty pattern. You'll see it used in plenty of other things. In particular, if you take 482, you'll see it with lock acquisition and lock freeing. Here's a really nifty example, I think. So let's say we have some cout flags that we want to set. I think in project, I guess just project 4 actually, we have the precision for cout set to 2, so we don't print a bunch of decimals on the end of your tours. So say we wanted to set that precision, but we only wanted to set it for one function. What we could do is save the old precision, before we change it, and then after we change it, set it back. But a more fun way to do it is to write a class that does it for you. And in the constructor, we are going to store the old flags and the old precision. And in the destructor, we're going to restore the flags from what the old flags were and the precision from what the old precision was. So in this function, clearly we want to mess around with the precision and some flags. So we're going to first declare a cout format saver, which is going to store whatever cout settings were at this line of code. Then we're going to change them. And then as soon as this function returns, right at this curly brace down here, we're going to restore automatically via the destructor of cout format saver. The old settings are going to be restored, which is pretty nifty. And additionally, another justification for using RAII is that it's exception safe and that destructors are called even if the frame is left through an exception. So even if we have some function that could throw here, we can rest assured that no matter how we leave this function, our old settings for our cout formatting will be restored. So skipping ahead, this is not important at all. Let's look at lambdas in the functional library. I'll pause for like a minute to see if anybody has any questions, but other than that, we will be moving ahead. Cool. All right, so let's look at lambdas in the functional library. Oh, I thought exceptions cause destructors to not run, or is that exit 1? Exit 1, I think, is what you're thinking of. And I recently learned, actually, I don't know enough about that to even say what I was thinking. But exceptions always trigger destructions of local variables to run. That is a guaranteed thing that you can rely on. Exit 1, I believe, does not, but I mean, if you're using the exit function at all, you probably don't really care about the state of memory in your program because you are about to exit the program. Yeah, but that's generally seen as bad style. You generally want to kind of end your program from the same spot. And one way to do that is by throwing an exception all the way to the top level of your code where you can handle it if you want to. Is exit 1 any different than return 1 from main? Yes, for the reason actually I just mentioned, and possibly for other reasons. But if you're returning one from main, that means that you are destructing all of the local variables for the current frame, and at the very least, that's the main frame, or the frame for the function int main. But if you were to exit one from main, then the local variables to main would not be destructed. And if you were to call it from a different function, say, those locals would not be destructed either. Why does it matter if we destruct variables if the program is ending? Doesn't a program ending mean all of its memory will be deallocated? That is a question that I do not have the knowledge to answer. If somebody in chat has an answer, then that is probably more than I know. My answer is good style. I don't know. Maybe there's a reason, but I don't exactly know it. Yeah, no problem. Yeah. Okay. So let's look at lambdas and a little bit of the functional library, but I expect I will skip the functional library stuff. So lambdas are just anonymous functions. Sometimes we write functions that we only use in one place, and we don't need to give them a name. We don't necessarily need to, put them at the file scope. We usually just want to, in these cases, we just want to have a function that we're going to use once. So if we do, then why don't we have a way to define these functions in line? And I think a great justification for this would be we've written a lot of comparators in the projects in this course, and these comparators are usually only used in one place. So if we want to, why don't we define these comparators right in line? So if we have a standard sort call, why don't we define the comparator right in the standard sort call? And lambdas allow us to do that. Basically just shorthand for writing a function, and you can do them in line, which is super, super convenient. Yeah, and C++ doesn't allow you to create functions within functions. Other languages do allow you to do that. I would say, like, notably Python and JavaScript are very geared towards that sort of thing. But C++ does not. So if we wanted to create a function, we would have to do it outside of the current function scope, which is going to potentially pollute the namespace. So lambdas are anonymous functions that can be defined and used similarly to function objects. Anonymous because by default they're nameless, and they are usually not stored, but they can be stored, I guess. Gabe says, as far as I know, it's not super significant for programs that terminate. When this matters most is for programs that run for a long time, like an operating system. Yeah, that makes sense to me. I guess especially if you had sub processes. So if we have an OS that has a ton of other processes that are running off of it, and the sub processes exit, maybe because the main process is still running, those sub processes memories, the memory of the sub processes not getting cleaned up would maybe have some effect. That makes sense. I could accept that justification. Okay, so lambdas. Here is the anatomy of a lambda, which I think is super, super cool. We have first in square brackets something called a capture list. Then in parentheses, we have the parameters to the function. Then in the curly braces, we have the body to the function. And everything except for this capture list out front probably looks more or less like a normal function. And the capture list is, you can kind of think of it as being member variables that the lambda has. So if we're thinking about lambdas as function objects, you can think of this capture list as kind of being a constructor that takes in and stores some data that the body of the function can use and modify as it wishes to. And we'll see later that this is actually a lot more powerful than just what it seems. But yeah, we'll look at that later. So if we have this function here, like I said, we have a comparator. We just have some item, and we just want to return if the item's x value is less than the other item's x value. We would have some comparator function that's outside of the current frame, like I said, and we're just going to pass it to standard sort. But the way we could do this with lambdas is we define a lambda right in line, right in that sort call, which takes in the two items and returns the proper thing as a result. And you can see how this is much cleaner. And specifically, now this comp func function is no longer in this file scope when it definitely doesn't need to be because we only are using it in one place. So a little bit more on capture lists. Yeah, these are definitely one of the weirder things in C++. This is not, I would say, not super important to know, but if we want to go deep into capture lists, take a look at this slide. There's a Stack Overflow post that I've linked in the notes for these slides, but for now I'm going to skip this, and I believe I'm going to skip the next few slides as well, just because they're not super important. And that might bring us to the end of lambdas. So if anybody has any lambda questions, feel free to ask them now. I guess first I'll talk about trailing return types. But if we go back to our anatomy, remember we have our square brackets, then our parentheses for the parameters, then we have our curly braces for the body, and we never specified a return type there. But we do have to specify return types for normal functions. So what's the deal there? How come we can't get away with doing that for normal functions? Why do we need to specify return types? The answer is just that normally lambdas are simple, and normally they only have one return statement, and normally the compiler can very, very trivially determine what the return type of a lambda is. But unfortunately, as this bullet point says, this is not always the case. So if we have a function even as simple as this, where we have, we're taking in a double, and if d is less than 0, we're returning 0. Otherwise, we're returning d. The compiler is going to analyze this, and it's going to see this 0. It's going to say, we're returning an int in this case, but in this case, we're returning a double. So it's going to throw its hands up and say, I don't know what we're supposed to return here. This isn't going to compile. So yeah, Alan's pointing out in the chat that, yeah, we could definitely just say return 0.0, and this might work. I'm not actually sure. It might actually, the compiler might take a look at this and still see two return statements and throw its hands up. But either way, sometimes it's not as easy as just adding a 0.0. So what we actually need to do is add a return type explicitly with the trailing return type, which is, in my opinion, ugly. So you can do this for any function, by the way. If you want to specify, if you've ever seen an auto return type on a function, and the return type specified after the parameters but before the body, that's the same thing here. You can just do the little arrow after the parameters and specify the return type. And from there, the compiler will be able to tell, okay, cool. In both of these cases, we're returning a double. I'm happy with that. And then it can do the rest of its type checking like C++ normally does. Works. Great. Oh, yep. And here's the Stack Overflow post I was talking about. Yeah, one more weird thing about lambdas is you can capture, well, that's not right. It's just the auto type to store something, but you can actually capture a lambda in a variable, which is super, super interesting. And usually you don't really have an easy way in C++ of storing functions in variables. You normally have to do weird stuff with function pointers or with the functional library, which are going to be in the slides that I'm not going to go over, which are right after this. And anyways, with a line of code like this, if you have some variable that has the auto type, you can actually assign a lambda to it. And from there, you can call that just like you would call a normal function. And this is actually super, super interesting. And you can get some really fun code out of this where, say you only want to, say you have a lambda that you want to call twice in the same function, but because it's just in the same function, you don't want to create a function out of line to do it. You can just create a lambda, store it, and then use it twice within that function. Very nifty stuff, in my opinion. If you want to go more in depth about all that capture list stuff that I talked about, I would recommend reading the Stack Overflow post. It's honestly fantastic, and it goes over probably everything you're going to need to know. And here's a great line of C++ code. What's happening here is we have our capture list for a Lambda, we have our parameters for a Lambda, we have the body for a Lambda, and then good question in chat, what's this last parentheses? This is just calling the Lambda. So like any other function, if you go to call the function, you need to call it with the list of parameters that you want the function to receive. So if you look up here to where we're calling function, we have to call it with parameters and we have to give it 5 because it takes in an int. But because we're defining and using it on the same line here, and because it actually takes in no parameters, we can just pass this temporary Lambda object no parameters, and it will call this Lambda. So this is a line of code that effectively defines an anonymous function that does nothing and then calls it, which effectively also does nothing, but is pretty funny. Cool. So this is all I've got on Lambdas, and we have some more stuff on the functional library that I am going to regretfully skip. To be clear, though, I think this stuff is not super important at all. If you want to do functional programming, honestly, C++ is probably not your language anyways. You're probably coding in, I don't know, something Lisp-esque or something Python-esque. So I'm going to skip over that. Any questions? And just to be clear, these first, I guess the first 2 topics were by far the longest. These last ones are not nearly as long, so I'm expecting we'll be pretty fine. Our lambda is pretty much the same as using block scoped struct functors. I would say yes. So you cannot define functions in line, but you can actually define classes and structs in line. So if you want to, instead of using lambdas, you can definitely define a function class which has parentheses operator and it has a constructor which maybe takes in some data and modifies it. You can do all of that and put it in a block of code and then just use that functor. And that will give you can always get the same effect from a functor as you can from a lambda. And I actually believe under the hood that lambdas are just implemented using function objects. So yes, you can pretty much do the exact same stuff. Cool. So Variadic Templates. Basic idea of Variadic Templates are it's a template or it's a function that can take in any number of arguments. And the idea is that in the body of a function, we're going to process some number of the arguments, and then we're going to recurse with the remainder of the arguments. So already, let's just take a look at some code because I think this is the easiest way to take a look at what's happening here. One, I guess, question really quick for you guys. Can you guys see my mouse when I'm like mousing around on screen or not? Yes, cool. Awesome. I was relying on that earlier for like pointing at stuff, so I'm glad to see you can. Okay, so let's look at this bottom definition here. We have a template which is necessary for this. Even if we know what the types of the function that we're going to receive are, we need to template this function. So we have specifically we need to template the variadic argument, which I'll talk about in a second. But we have in this print function, we have the first object, which is some object of type t, and then we have this object args of type args ... And this is not really something that you're going to see anywhere else, this ... syntax, and it's just reserved for the specific case of what C++ refers to as a parameter pack. So you can think of this as storing the rest of the arguments to this function, but the first argument is kind of pulled out into this t first parameter. So what we're going to do is we're going to print the first argument just normally, just print it with whatever the operator arrow error or the operator less than was actually going to do, and then we're going to print a space, and then we're going to recurse with the rest of the items. So important thing to note is that because this args item is of a variadic type, so it has a bunch of types stored in it, we need to unpack it before we recurse on the next one. So thing to note, let's just look at the example here. If we print 4 different things with this example, what's going to happen is the first time we call this function, we're going to get this first item is going to be equal to the a string literal. Then args is going to have the int 5, the int 3, and the string literal apple in it. Then the second time we recurse with args, or we recurse on print, the first item is going to be the int 5, and then args is going to have 3 and apple, and you can see how that would work till the end. And one thing to note is that you do actually need this base case of where there's only one item and no args. Actually, now that I'm saying that, you might not need to. So one thing where I don't actually know completely down to the last detail what's going on here, but you might be able to get away with not having this definition, but it is important sometimes because in this example here, we want to print the new line at the end. So we actually do want a specific base case function. But I don't know. Play around with it for yourself if you want to see if you can get away with having an arg list that actually has nothing in it. Oh, and actually, totally disregard that. I think you do need it because if we were to call print on args ... but args had nothing in it, then this would surely cause a there would be no matching function call for this. So yeah, I think that would be how that works. Question from chat. Just to solidify my understanding, is 1 plus 2 in the main function an R value, whereas the 3 that's being printed in args an L value? Yeah. Okay. So yes, this 1 plus 2 is an R value. Yes, like you said. And the 3, which this evaluates to, is also an R value. But as soon as we enter the context of this function, as soon as we give that value of 3 a name, yes, you're correct, it is an L value at that moment. So similarly, this A here, just because it's the first one and it's easier to explain this A here is an R value. But as soon as, it becomes this value first, it becomes bound to this variable first in this function, then yes, it is an L value at this point. Cool. Yeah, good question. So this is how variadic functions work. I think I have another example here. Oh, yeah. Past me is smarter than present me. Yeah, the code will not compile if we do not have this base case function because eventually we will recurse with 0 unpacked args, which does not match any function signature. Cool. Glad that I put that in there. And rather than just doing one function or one argument process in each call, there's no reason you can't do more than one. So if we have, say, a similar function that instead of just printing something, we want to print pairs of things, then this would be how you'd set that up. You unpack 2 of the parameters in the first, not in the first. You unpack 2 of the parameters, and then you have the rest of the parameters stored in this args parameter pack, and we print 2 of them, and then we recurse. We have this base case which takes in 2 objects and prints both of them, and then prints done. So if we call it on 4 items here, we're going to see the first 2 are printed together. The last 2 are printed together, and then we're going to get done because that's what happens at the end of our base case. Yeah, and the important thing to note here is that all of this, like everything in C++, is checked at compile time. So if there's no matching function call, we will know it pretty darn soon. So for example, if we call this print pairs function with 5 items, what we're going to get is at the end here, this print pairs, wow, I misspelled a lot of stuff on these slides, but this print pairs recursion at the end is going to recurse eventually with 1 item. It's going to just recurse with sauce. And there's no matching function call for just 1 item passed to print pairs. So yeah, the above code would call. It doesn't actually call it, but the compiler is walking through this and checking what would be called. So it would call string, int, and then the parameter pack of int, string, string. So that's legal. That one checks out. Then it would call int, string, parameter pack of string. That's also legal. That checks out. Those would both match with this bottom definition here. Then we have the final one, which would be print pairs with just string. And that doesn't match with this one, and it doesn't match with this one because there's only one argument. So no matching function call. Compiler would detect this and throw an error, which is pretty nifty. Cool. Anything on Variadic templates? I think that's a pretty brief one. And if you wanted to, I'm sure there is probably one Stack Overflow post that you could read that would give you all the information you need to know on it. If you want to hear an actual use case for when I've used Variadic templates, in 482, if any of you take 482, you're likely going to want to do a lot of debug printing. And also in 482, if you want to make sure that your printing is deterministic, you're going to need to lock C out before you do any printing. So you can use Variadic templates to write your own Python-esque print function that takes in any number of arguments and acquires and releases the lock the first time that you need it, and releases it after the last time that you need it. That probably won't make sense unless you've taken 482. Question from chat: printf would have to use them, right? Yes. So yeah. So the only thing that's different there is that C printf is a C function. So I don't actually know what the C equivalent of Variadic templates are. But if you were to write printf in, a C++, the modern C++, you would use Variadic templates. Yeah. But yeah, I don't actually know what the C version of Variadic templates are. Maybe they use something like void pointers to get around it. Cool. I am stoked to talk about tries because I think tries are the coolest thing ever. And this is not a C++ specific thing. This is just a data structure. Let me get some water real quick. So tries, they're a node-based data structure specifically for storing strings. And you can extrapolate this idea to store things other than strings, but you'll see pretty quickly why they're useful for strings. They're very simple design. They're extremely efficient in insertion and lookup, better than hash tables, and I think they are just dope. And pronounce a try. I don't make the rules. I'm just reporting. What I've been told. So the design of a try, instead of storing words separately, we store just characters. So the words that have overlap don't store duplicated data. And an example here, if we want to have, say we have a hash table and we push app into it and we push apple into it, then this prefix app is duplicated across these two words. We'd be storing app twice. We'd store it once in app and once in apple. And with a try, we can get away with not duplicating this data, which I think is super clever. So yeah, this is kind of the structure for what a try looks like visually. And all we're storing is the characters, and we're storing whether or not each node is the end of a word. So in this example, we can see that APP is a word because the final P is denoted as a terminal. It's the end of a word. And similarly, APPLE, apple, is a word because this E is a terminal node. Question from chat, what would the root node in the example? Okay, yeah, the root node in this example here, you'll see, but it doesn't, it's just a special node that doesn't have a character associated with it. That's the only difference here. And you will see once I give a larger example as well that, you know, each of these nodes doesn't need to just have one child. It actually can have up to 26 children, which is kind of how this whole thing works. Well, let's take a look at that in a second. Okay, my animation there was busted. But for each letter, for each of those nodes in the previous example, we're going to store whether or not it's the end of the word, and we're going to store pointers to the n possible children nodes. So usually n is equal to 26. If we're just storing lowercase English letters, I would say that's by far the most common use of tries. And if you don't have a limited set of characters in your input set, then tries are not really going to have the value that you would expect. I think of this as being similar to a counting sort idea, where you want the input set to be small in order for this to be as efficient as it can be. Yeah, so that's what that bullet point there means. And then if there isn't a child for any given, there isn't a child for any of the given, I guess, letters, then you don't need to store a node. You just store a null pointer. So we can get away with not unnecessarily allocating things. So let's say we have a children array here. Let's say this is the root node of our tree. We have, you know, pointers for each of the lowercase English letters, and these would all point to child trinodes, or they would be null pointer. And to me, this makes a little more sense when we see it in action. So let's say we insert app into our try, and this is the root node. So it doesn't have a letter associated with it. It's just the root. So first thing we're going to do is we're going to allocate the child array to have all 26 slots that we discussed earlier. These are all going to be initialized to null pointer, so they start off as having nothing. But soon you're going to see we're going to add stuff. So because we inserted app, first we're going to insert a into the root. So now we have an a node. And I guess from there we still have the p and the p to allocate. So we need to allocate this children array. And I've nicely carved out a little slot for the p to exist here. And we're going to allocate a new try node for the p. And similarly, we're going to allocate another, allocate the children array for the p node because it still has another child to go. We have another p. And I believe I shrunk everything here. Good. And then we allocate this array. And of course, we need to allocate the second p node. So that's what's going to happen here. And we don't need to allocate the children array for this one yet. And of course, this is the end of a word. So we're going to mark it as such. And that will finish up this insertion. So what happens when we insert bat? You're going to see a very similar thing. We're going to go to the root. We're going to see B currently has no words starting with B from the root. So what we're going to do from there is we're going to allocate a new node, and we're going to point to it from the root children B slot. Then allocate the children array for the B node. We have nothing in the A slot, which is the next character we're looking at. So allocate the A node. And then, of course, similar thing to allocate the final one. Then if we insert apple, we're going to look at the root node. We're going to see we actually already have something in the A slot. So we look at the A node. We see we already have something in the P slot after that. So we look at the next node. We already have another P in the slot after that. So we look at the next node. And we'll see that there are no children here, so we have nowhere to put the LE. So let's allocate the children node for this P node here. And from there, we can create the L node, allocate children for that. And then we can create the E node and specify that that's the end of the word. Hopefully I muted in time for that cough. But you can see how the example I've chosen here is kind of like two sticks going down. But you can imagine how this would be, there's potentially 26 children going off of each of these nodes, right? So if I had, I don't know, a word that the word ape, right? So we would go A, P, and then there would be an E node here that maybe points to, or sorry, there'd be a pointer here that points to an E node that would, store the E, and we would have our word ape as well. So, any questions on the idea of a trie? This is pretty much all there is to it. We can talk about time complexity and stuff on the next slide, but implementation-wise, any questions? Cool. Let's move on. So complexities. And I'm sure a lot of you are seeing this and you're saying, wait a minute, I thought these were fantastic. Isn't a hash table just better than this? So first let's think about why is this the way that it is? Insert, lookup, and removal are all O of K, where K is the length of the string. So this makes sense to me intuitively. If we want to insert or look up a word, we need to, check each node according to the character that we're looking for. And then at the very end, the last step would be, is the ending character that we're on the end of a word? Right, so if we're looking for the word, I guess let's assume AP is a word. If we're looking for the word AP in this tree, what we would do is we check for A, then we check for P, and we would say, yep, we have a P, but this isn't the end of a word. So the word AP is actually not stored in the trie. But either way, the big idea is that we need to check the number of characters equal to the length of the string. So O of K time for that. Insert and lookup, that makes sense. In removal, you could think of this. Let's see if I did, yes. So removal, you can say, find the word and just set the end bit to false. So if we wanted to remove apple, we could just find the word apple and then set this E to false. And this, I would say, would be a very common way of implementing removal, but one could argue, and I would say possibly rightfully so, that this is wasteful of memory because if we delete apple, we could actually delete this LE chain on the end of this leftmost chain here. So the other way you could do it, if you actually want to remove letters, is you could recurse back up the trie after you found the word, and if there's no other children and it's not the end of the word for each given node, so starting with the E, we would delete the E, then we'd go back up to the L, and we'd say, if there are no other children and it's not the end of the word, we can delete the node and recurse up. So L has no other children besides E, and L is not the end of the word, so we can delete it, and we can move back up. Then we check P. Does P have any other children? No, it does not. It only had L. Is P the end of the word? Yes, P is the end of the word, so we cannot delete P, and thus our recursion is done and we've removed it. Either way, though, at worst, this is going to take O of K to go down the tree, and then at worst, it'll take O of K to go back up the tree to do this recursion, so this is still O of K. And I think, okay, yeah, this is just pseudocode. Obviously, there's edge cases, blah, blah, blah. No accountability if you implement this and have a bunch of bugs. Yeah, this is what I was wanting to talk about, though. These are the theoretical lower bounds for a string data structure for these three operations. You cannot actually get better than this in terms of big O complexity. So what I was talking about earlier is that hash tables we say are O of 1 insert, lookup, remove, but really those are constant time, not counting the amount of time it takes to hash the object. So in order to hash strings, you do need to actually access each character in the string, which makes them O of k to hash. So really, hash tables are O of k for all these operations as well. And in practice, they're going to be a lot slower than using a trie because of the overhead of doing things like, actually hashing, calling a hash function. So things to consider: heavy memory overhead, because we have an array of 26 pointers per node. And even though we don't allocate it every time we need to, I mean, in this case here, for this tree specifically, we have a lot of wasted space. Our A node, actually, each of these nodes, except for the T and the E, have 26 children, and they're only using one of them. So you can think of that as being, 8 bytes per pointer times 25 times 1, 2, 3, 4, 5, 6, I guess 7 because the root nodes. So quite a lot of wasted space here, but whoops, I guess that was the last slide. But very, very fast. And if you're into the whole interview questions or maybe leak code or whatever like that, which you certainly don't need to be, but I have seen these come up a few times, and I think it's an interesting thing to know. Even if they're not easy to, code up on the spot, it's something where you can explain maybe to an interviewer that you know a way to achieve X complexity. So yeah, any questions on tries? Cool. I am going to move on. Polymorphism under the hood. I'm gonna breeze through this. I guess I don't even know. Yeah, I'm gonna breeze through this because I think this is not a super important topic to discuss unless people are super into object-oriented programming. So I'll go super quick here. We say that in hierarchies for any object-oriented programming language that the child class object or child class objects are parent class objects. So wherever a parent pointer is expected, we can use a child pointer instead. And this is something that I believe was explained in EX280 as well. But the main question of this that I want to answer here is, why is this the case? What's kind of the under the hood of how does C++ implement object-oriented stuff? How do they implement objects in a hierarchy? How are virtual functions working under the hood? So what objects look like in general is they are as efficient as they can be. They just are the data members stacked up as tightly packed as they can be. And then any pointer that's referring to an object that exists in this faction just points to the beginning of the object, and the data members are accessed via just byte offsets. So ints are 4 bytes, so we know that the first field of any A object is just in the bytes 0 to 4. The second field will be stored in the bytes 4 to 8, and then the third field, because it's a double, will be stored in the bytes 8 to 16. I chose a nice example here, but if you've taken 370, you'll know that there are some asterisks with padding and things like that, especially if you're not using things that are even 4s and 8s. So they are contiguous in memory, sometimes padding. Data members are stored in the order specified in the class definition, and we access them via byte offsets, and the pointers point to the beginning. Already said all that. So yeah, getting the A2 field will grab bytes 4 through 8. Great. So if we have an object in a hierarchy, so let's say we have a B object that is inheriting, or a B class that inherits from the A class. So a B object really has all of the data from the A object, and it has all the data from the B object. So in memory, this looks exactly how you would expect it to. It's just the data members for an A object and then the data members for the B object right at the end of it. And still, getting the A2 field will just get bytes 4 through 8 from the underlying representation. So this isn't, there's no difference between an A pointer and a B pointer in this way, and this is why we can say that, our child class pointers are just parent class pointers, because quite literally they both point to the same spot. So there's no reason that if you wanted to do anything on a B object anything on an A object, that you couldn't also do it on a B object. And I think the easiest way is to just know the pointers literally point to the same spot in the object. Great. So that's that. I think that's very simple. Virtual functions. I'm not going to get super in depth of this. Basics of virtual functions. If you call a function through a pointer and the function is marked virtual, you are going to get the most derived version of that function. So this is maybe something you remember from 280, but if not, you can take a look at that slide after and get a feel for it. I'm not going to go over this example. I do have the output there if you want to take a look at it. And I believe in the replit that I linked earlier, I have a similar thing there where the example is listed out and you can play around with it. So how do virtual functions work? What's the overhead? The virtual function table is how C++ implements virtual functions. And the big idea is that each class has a table of the virtual functions that it defines. And for each object in the class hierarchy, we keep a pointer to that table. And the pointer is initialized behind the scenes during construction, and it points to the V table for the most derived class. So let's look at an example for this, because I think this is how I work best, and I think this is how this stuff is best explained. So let's say we have our A struct and our B struct again, but this time we have functions. So let's say we have, in the parent class, the base class here, we have a virtual function foo and a virtual function bar. And then in the child class, we have foo, which is, even though it's not marked virtual, it is overriding the parent class version of foo. And we have a new function, baz, which is marked as virtual in B. So here's what the V tables would look like for these two classes. So the V table for class A, it's going to have an entry for foo and an entry for bar, because those are the two virtual functions that it knows. And for B, it's going to have one for foo, one for bar, because that's what it inherited from class A. And it's also going to have one for baz, because that's the one that it declared in its definition. So this is what the V tables look like for these two classes. And if we look at, what an object looks like, what a C++ object in a hierarchy looks like, if any of those objects in the hierarchy have virtual functions, this is what they're going to look like now. Is that we have this V pointer, this hidden V pointer field, which is actually the first data member of the object itself. And it points to the correct V table given the object. So let's say we have an A object here. We're going to have just the data members for the A class, and we're going to have a V pointer that's pointing to the V table for class A. So because we have an actual base class object here, this isn't really that fancy, because if we want to call foo, what's going to happen is we're going to look through the V pointer. We're going to see which version of foo should we call. And of course, it's going to be A's version of foo, because we're in the base class. There's no derived class version to use. And similarly, if we want to call bar, we're going to look through the V pointer and see which version of bar should we call, and we're going to call A's version of bar. Where it becomes interesting is when we actually do this with a child class object. So during construction, the V pointer is going to be initialized to point to B's V table. So we still have all the data members stored just how we expected for the previous example. But now, if we want to call a virtual function in the hierarchy, what we do is we go through the V pointer and we can call the most derived versions of the functions. So you say if we want to call foo on a B object through a pointer, so it has to be a virtual function call. Go back a few slides if you want to see exactly what a virtual function call means. But if we're calling foo virtually, then we're going to see that B's version of foo will be called. And if we look at this, this is actually correct, because It's a virtual function of the base class, and we overrode it in the derived class. And then for bar, we're going to get A's version of bar because it was marked virtual in the base class, and we didn't override it in the derived class. So that looks good too. And then Baz, which is the new entry, which we didn't have in A's V table, which is of course going to get our B-defined version of Baz. So this is how that is all implemented under the hood. The important thing to know is that these V tables are generated at compile time. So just by looking at the code, without creating any objects or generating anything, just by looking at the code, the compiler can tell exactly what versions of each function should be called for a given class. And that makes sense because you always want to pick the most derived version you have access to. And if we have a B object, we can tell right away we want to use the versions. We want to use the B versions for everything it can. Otherwise, we're going to use the A versions for everything we can. Otherwise, if there was another base class, we'd use those versions for everything we can. So that's how this all looks under the hood. This is the engine for C++'s polymorphic function calls, and the runtime overhead is just a pointer dereference and an array access. The memory overhead is that we do need to store an additional pointer per object. Importantly, though, if you have some kind of class hierarchy that doesn't use virtual functions at all, then there's no v pointer stored, so you're not losing anything by just having normal class objects in a hierarchy. Cool. This is also, in very C++ fashion, this is very efficient. I think other, for example, Python virtual lookup, not virtual lookup, but Python like polymorphic function calls, it works more or less through a runtime maintained dictionary, which is just a hash table. So in Python, what would happen is, let's go back to our previous example, I guess. In Python, what would happen is instead of a v pointer, this object would have a dictionary of names to functions. And if we wanted to call foo, it would do, functions dot find, or whatever the hash table lookup would be, functions square brackets foo, and that would return the foo function that should be called, and then it would call that foo function, which is notably slower than just doing a pointer dereference and an array access. Anyhow, not knocking Python because there's plenty of practical reasons why you'd want the runtime function dictionary that they use. That is certainly not a topic for today. And then super briefly, if anybody has any questions, feel free to drop them in the chat, but I'm trying to speed through this lickety-split. Super briefly, structured bindings in C++. This is just a quality of life thing. This is not going to change your code significantly. It's just a fun little thing that you can use to make your code a little more readable and a little less nasty. So if we want to return multiple values in C++, like in Python, what you can do is you can return, not just Python, and a lot of other languages, but as an example, in Python, if you want to return multiple values, you can do something of the form return, 1, 2. And it's going to return two values, the value 1 and the value 2. And you can do this for any number of values. They don't even have to be the same type. It's great. It's fantastic. In C++, this is not possible. If we want to do something like this, we would have to do something ugly, like declare a std tuple of int, int, and then return the tuple with like return make tuple of 1, 2. Pretty ugly. I don't think it's that great, but it's as close as we can get in C++ without using structured bindings. So we can come pretty close to approximating multiple return values if we use structured bindings instead tuple. So yeah, if you wanted to do multiple return values before structured bindings, you could do any of these things, which are all sufficiently ugly in their own right. But if we have structured bindings, then what we can do is we can return a tuple-like object, and we can unpack it on the fly into a bunch of different variables. And with this, we can have a budget version of multiple return values. So here's the anatomy. Type, then we have square brackets, and we have name of the variable, dot, 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 as many variables as you need. And you are going to assign a tuple-like object into it. So normally this is going to look like auto and then a list of variable names that you want to create for these tuple objects. So this is, I think, a great example here. I think these are actually all from CPP reference, if I'm remembering correctly. Yeah. So the insert function for hash tables returns an iterator to the inserted object and a Boolean determining whether or not the insertion was successful. So what you do, what you could do is, because that is a tuple, you can assign it to this structured binding, which has the type auto, and it's going to initialize this iter thing, which is not yet a variable, but after this line it will be a variable. It's going to initialize the iter with the iterator pointing to the newly inserted object, and it's going to initialize success with the Boolean denoting whether or not the insertion was successful. So these don't have to be the same type or anything. We're using the auto keyword here. Iter is now a std iterator. I mean, specifically, it's going to be a std, whatever, unordered map of string to, I don't know, int or something, : iterator, but it's just an iterator. And success is going to be a Boolean. So we can do that with anything that looks like a tuple. We can also do it with a struct, which is, I didn't know you could do this, but this is pretty cool. You can declare some struct object, and then by reference, you can capture new, or by reference, you can unpack sort of tease fields into these new variables h, m, and s, and then you can set, if you set h in this current frame, it's the same thing as setting t dot hours, which I think is pretty cool. And then similarly, kind of the idea I just talked about, if we have a function that returns a tuple, we can make variables which correspond to the return value of the function using structured bindings. All right, this can also be used to unpack array values, just other stuff. All in all, though, this is just a nice quality of life feature. There are not many of these in C++, in my opinion, so we take what we can get. Cool. So that is finally, let's see what we clocked in at. Just over 2.5 hours. I guess that's not too bad, but still an excruciatingly long lecture of extra stuff in C++ that you may or may not use, but I think is at the very least very interesting. So any questions at all, feel free to fire them off, but totally understand that this is a long one. And if that's it, then, I mean, I hope you all had a great experience in EX281, and I wish you all the best of luck in your future classes. If you're graduating, congratulations. I wish you the best of luck in whatever your future holds. And yeah, for the rest of you, maybe I'll see you on campus in fall of 21. Yeah, thanks. Thanks, everybody. Thanks, Yue, Andrew, William, Mert. Yeah, one question. Where did I learn all of this? So I would say that I learned, man, let me look at the agenda really quick, actually. I can give you an exact breakdown. So move semantics, smart pointers, RAII, lambdas in the functional library. I learned all of this I learned these and these in EX381, which is not offered anymore because the professor, Dr. Curis, actually retired. Fantastic class, a ton of work though, and yeah, nobody else wanted to teach class because it was so much work for the professor that I don't think it will be picked up again in the near future. Yeah, so another question building on that, you mentioned 381 before. Do you recommend going through the previous course content as the class got removed? So, I mean, yes and no. I think the content is fantastic. I think, frankly, a lot of the benefit from the class um, you could pick up from these slides alone, but an even bigger part of the class was um, that Professor Curis hand graded your code for all 7 of the projects, and he would go extremely hard on design decisions and style, which is not something that is really graded in at least any other class that I have taken. There's a little bit of style grading in classes like 482 or programming languages, but it's not that much. Um, very, very, very good for things like code maintainability and not duplicating code. Things that are just in general good for code that other people can read and understand and update, which I think is probably very important for industry. That said, you're not going to get any of that from the course content on the website. That's kind of just something you would get from him hand grading your projects. So that's something you'll miss out on if you do the online stuff. Um, the second thing I would say would be the design aspect of the course. And there are a ton of different design idioms that he goes over, which are on the course website. You can go through, I think there's like 3 different PDFs, which are like 30 pages each, which go through a bunch of different design idioms, which are all fantastic to look at. Where's the course website? Let's see if I can find it. EX381. There we go. Look at that. No HTTPS needed. Love that little red squiggly. Yeah, I'll put that right there. If you want to try to figure stuff out, let's see if I can find some stuff. Handouts. Where are the lecture notes? Maybe here we go. Yeah, these are the 3. These are the 3 like design patterns PDFs you can look at. Super interesting stuff that you will see. That you will certainly see if you're taking a look at any industry code. Stuff like model view controller, singleton idioms, mix-in idioms. I don't know. There's a lot to look at there, so take it or leave it. I would say you can definitely learn a lot of this stuff if you're going into industry just by being on the job and absorbing information. So definitely not necessary, but if you want to maybe impress some people, you can do that. Anyways, those are the kind of benefits of 381. Totally up to you. There's a ton of reading that you just need to absorb, and a lot of the learning, at least for me, was gathered through the next day in class after you did the readings. There would be a professor orchestrated discussion of the content. So that's not something you're going to get either. But the readings are all fantastic. He writes up things better than you're going to find on CPP reference, better than you're going to find on any Stack Overflow post. He has written them concisely. He's been doing it for so many years. So all of his readings, I think, are great. To finish up the first question, though, Variadic Templates. I don't remember where I learned them. Maybe, I don't know, that's maybe something I just looked up on my own. Tries. I don't remember either. Maybe somebody told me about them. I think they're pretty nifty. This is probably somebody mentioned it on staff once, and I Googled them, and I thought it was fascinating. Structured bindings, I didn't know until the semester. Joe Richards on staff made a note of them, and I said, oh, that's interesting. And then I looked into them, and I said, oh, that's really cool. So that's where I gathered all this stuff. Really, though, this isn't like, I'm not some like super genius or anything. I just picked up this as I programmed, and as you program more in C++, you'll see some of these things organically, and you'll just pick them up. So even without EX381, you're not going to, I mean, you will eventually run into all of these topics and learn about them. Cool. One more question. What would be some good things to do, like resume projects over the summer? Like some things that could help build a personal portfolio? Yeah, so I think, I mean, I'm not like the best to, I'm probably not like the best person to just ask about this, but one thing that I can definitely say is the university itself is good at helping with things like resume building. I know the Career Center. I'm sure there's one for LSA, but I know the College of Engineering has a great Career Center. If you want to reach out and talk to people about that, they do resume reviews, which are free. I know they do workshops and stuff like that. And also, I think Mark Brehab, which is one of the 370 professors and a 470 professor as well, sent out an email recently with a bunch of professors that are looking for students to help with summer projects. And some of them are paid, and a lot of them you can do for student credit, actually. So if you're interested in joining some sort of project over the summer, um, getting to know a professor and doing something with a professor, I would say, is a huge thing that you can do. So yeah, if you want, I would either take a look in your email if that, yeah, perfect. Awesome. William just put the link in the chat for that. Yeah, so take a look at that. I would definitely do that. Cool. I think that is all the questions. Yeah, so barring any last minute squeakers, we are going to call this the official end of EECS 281. Yep, great. More resources in the chat from Ethan. Yeah. Yeah, no problem, everybody. Thank you guys for coming. I'm surprised everybody showed up. I would have expected this to be a very small, if not zero, group, but this was a lot of people. Yeah, no problem. So I'm going to end the recording here. If I can figure out how to do that.